Hello guys, so welcome back to our lecture 17. This is basically the last video in this lecture. And we're gonna, continue with the same example, but we're gonna deal with it in approximate way. So last time we did the iterative solution. It takes time for us. Although for that particular one that we solved, it was just 4 or 5 steps, very short, but it might take longer. It's not guaranteed all the time that it will take, this short time or short, number of steps. Okay. So again, like the constant voltage model for the diode, we can apply the same principle here. So in the constant voltage model for the diode, we said that whenever a diode is forward biased and on, VD will be 0.7. Or based on the the diode type. It may be if it's for example germanium, it will be 0.3 and so on. Okay, so we're gonna apply the same principle here as well. Okay, we're gonna assume that we're gonna make some approximation basically that whenever G1, the base emitter junction, is forward and on, either in forward, either in active or saturation, the voltage VBE will be 0.7. Will be fixed basically. So some box you will find that in the active region it's 0.7, in the saturation it's 0.8, but basically it's a fixed, it's known basically. Once you know the operation region, so it's known. So we're gonna apply this principle here as well, or this approximation basically here as well. So in that same example that we did iteratively last time, okay, we're gonna solve it now using that approximation. So we know it's in active region. So we know that G1 is forward. So since the transistor is in active region, so we know that G1, the junction between the base and the emitter, is forward and on. So we're gonna assume that VBE equal to 0.7 volt, fixed. And let's now compare it to the value of VB that we get from the iterative solution. So if we did this in red, it was 6907. And now look, just to compare them, this is from the iterative solution, and this is just by approximation. They are very close to each other, but it's not that case all the time. So you might have some error between 10% to 15%, 20% maximum, okay? But it will be in that range, which is acceptable, So this is for VBE, just in one click, since you use this approximation, then it's solved, it's known now. Now let's continue. Since now you know VBE, remember that our basic problem in this example or this circuit is that IB is not known. Okay, now if we know VBE, which is 0.7 now, based on our approximation, can we determine IB? Yes. And I'm gonna now solve the circuit without using the the equivalent circuit that I showed you last time. I said to you, you can use it, of course, it's really correct and working, and it's also perfect. But basically, you don't need to waste your time. You can solve the circuit basically without replacing the transistor with its equivalent circuit. It's really easy. It's not that complicated. So let's do that. In our circuits, we deal with, devices by using their terminals. So the transistor has 3 terminals. This terminal here is the base. This terminal here is the collector. This terminal here is the emitter. Okay, that's it. And the emitter voltage is basically 0. It's connected to the ground, which is really nice. And now see, you said that VBE, the voltage between the base and the emitter, is 0.7. So that means that VBE minus VE is 0.7. So from that, since VE is 0, so VB is 0.7. So this is basically 0.7. The point here is 0.7. And remember, IB is the current that is going into the base. So you can determine IB easily using the terminal voltage of this resistor, 431 kilo ohms. So it's 5 minus VB over the resistor RB. So 5 minus VB is 0.7 over 431 31 kilo ohms. Okay, so usually IB is really small, so you will find this is the case all the time. So this will give us 9.976 microamperes. Micro, it was really small, so I converted it to microns by multiplying this, this term here by 1000. Okay, and the IC, which again we determined, iteratively last time, will be easily beta IB. Beta is 100, look, times IB 9976. Yeah, it will be 997.6 microamperes or 0.9976 milliamperes. And again, compare this to what we get iteratively last time. If we compare it, what we get was 0.9998 milliamperes. So compare them to each other. They are really close to each other. Okay, so this approximate solution is really good. It's really good. It will save your time. Okay, and in a very short time you can get the answers that you want without needing to calculate or heavy computations. You don't need all of that. Okay, but again, it's not the case all the time. I mean, this small error, you might again get errors between 10% to 20%, which is again acceptable. And now VCE, remember, in this example or this circuit, our two unknowns basically was VBE and VCE. VBE was determined easily, but just by using the approximation as instructed in the in the question head here. Okay, and now it's turn for VCE. Again, you don't need to draw the equivalent circuit. You can just deal with the transistor circuit without converting it to another circuit. So basically, IC, which is known now flowing in that branch here. Okay, and again VCE is equal to VC minus VE. VE is 0, so this is equal to VC. So if we get VC, we get VC. So IC equal to 5 minus VC, our unknown, over RC. 5 minus VC over RC, which is 3 kilo ohms, equal to 9976. From that, VC is equal to 5 minus 3 times 9976, which is basically 2009 volt. Okay, so if we compare it again to the ones that we get from the iterative solution, it was 9.0006. Very close, very close. Okay, again, you might not get such close results in all cases. I mean the iterative solution and the approximate solution, but again the error will be contained between within 20% range. Okay, which is acceptable in most of the times. Okay, guys, so from now on, we're gonna use this approximate solutions. I mean approximate assumption for VBE. We will not draw the equivalent circuit again. I'm not saying it's wrong. You can use it, of course. If you see that dealing with a transistor is hard for you, especially because you started working with transistor circuit right now, you can of course freely use it. But again, you should train yourself that it's not that complicated. You can just deal with a transistor with its symbol. No need to make equivalent circuit. Okay, thank you very much, guys, for watching this video, and see you in the next lecture. Bye-bye.